Hello students, we shall continue the chapter number 2. Today our topic is capacitance of a capacitor. Okay, so now our first page will have the quick points which you have to remember for the entrance of JEE and NEET, and the next two pages we shall understand other points which are also equally important for the entrances, but basically it will be a derivation part. So let us understand the quick points to remember for JEE NEET. As you can see here, I have drawn a capacitor with two parallel plates with a positive charge and a negative charge. Distance d between the two plates, and a is the area of each plate, and v1 and v2 is the potential for the plate 1 and the plate 2. This is the plate 1 and this is the plate 2. You can also have irregular shaped plates or the conductors. These are two conductors, 1 and 2. Fine. Okay, so the electric field between the two plates is from the plate 1 to the plate 2, which is positively charged plate 1 and negatively charged plate 2. Fine. So what you have to remember is the net charge for the capacitor remains 0. That is the first point. But for each plate has a charge Q. Potential difference V between the plates is V1 minus V2. And the capacitance C is equal to Q by V for this arrangement of the two conductors. Okay. Now this C is a constant which does not depend on both Q and V. It depends, capacitance C depends only on shape, size, and distance between the conductors. Fine, or of the conductors. So taking into the consideration of the shape, size and the distance between the conductors, as you can see, the distance is d, the size is a, is area. Okay, so depending on the shape, size and distance between the conductors, we have the formula C is equal to epsilon naught A by D. Okay, so these are the formulas which we will discuss in the page 2 and the page 3 of the same video. Okay, then some more points to remember is how to denote a capacitance or a capacitor in a circuit. Okay, this is for a constant capacitance C. If I have a variable capacitance, then I show one arrow on it, variable capacitance. These all are quick points to remember at a glance. Variable C, dimensional formula, C is equal to M minus 1 L negative 2 on the power T raised to 4 and A raised to 2. This is the dimensional formula of a capacitor, capacitance, capacitor's capacitance. Okay, and unit is 1 farad, which is equal to 1 coulomb upon volt. Fine. And normally we use 1 microfarad, which is equal to 10 raised to minus 6 of a farad. Then we use 1 nanofarad, okay, unit. So 10 raised to, which is equal to 10 raised to minus 9 farad. 1 picofarad, which is equal to 10 raised to minus 12 of a farad. These all you have to remember for the quick conversion from the given unit to a farad. Micro 10 raised to minus 6, nano 10 raised to minus 9, and pico 10 raised to minus 12. So quick revision has to be done before you actually apply the formula. For that, this page is made so that you remember these formulas very quickly. The formula of C, Q by V, C is equal to epsilon naught A by D, then its dimensional formula, then its conversions, then its symbol which will be used in the circuit, then its variable capacitance also which can be used in the circuit, and this is its construction part. One more formula you can remember is E, electric field between these two plates. You can see the electric field here from positive plate to the negative plate, positive charge plate to the negative charge plate, which is given as sigma upon epsilon naught. This also remember. Fine. So these are the quick points to be remembered for the entrance exams. Like JEE and NEET, there are other entrance exams also based on this topic. So quick revision for capacitance of a capacitor. Fine. After this we shall move to the next page. Take a pic here where we will be understanding how these formulas have come about, which are also equally important for the entrances because they can come for the assertion reasoning questions also. Fine. So keep watching till the end of the video so that the concept of capacitance of a capacitor is understood by you very clearly. Now let us understand what is a capacitor made up of. As you can see with the diagram, it consists of a conductor 1 and a conductor 2 with a space filled with insulator. Okay. Conductor 1 has a charge of positive Q on its surface and conductor 2 has a charge of negative Q on its surface. We have already learned inside a conductor there is no charge. Okay, there is no electric field. Potential is also same everywhere. Fine. Okay, that we have already learned. Fine. Okay, and the space between, say, is air, or it can also be a dielectric. Regarding this we shall do another video also. Fine. At present we are talking about air between the two conductors. This arrangement is called as a capacitor. Fine. Okay. So now as you can see, Q is charge of each conductor. V1 the potential of the conductor 1, V2 the potential of conductor 2. Potential difference V is equal to V1 minus V2. Fine. So between these two conductors there will be an electric field E, due to which there will be a potential V. Fine. So as the charge increases. Suppose we increase the charge double on these two conductors, the electric field also will increase, correct? Because of the formula we know. And so the potential will also increase. So we can say as charge increases, electric field between the two conductors also increases, and so the potential, each potential of the two conductors also increases. Fine. So we can conclude that Q, that is the potential difference, also increases. So Q directly proportional to V, or we can say Q upon V is a constant. That constant is denoted by C is equal to Q by V. So this is the formula of the capacitance which is a constant but does not depend on Q or V. But it depends, as I said in the previous page, depends on shape, size and distance between the two conductors. Fine. Okay. And its unit is farad. Fine. Okay. This I have denoted by F. This I have already explained in the previous page. Now, how much of electric field can a capacitor hold between the two conductors is called as the dielectric strength. So now we define dielectric strength. This is the maximum electric field that can be held between the conductors 1 and 2 without breakdown. Okay, that means without any leakage from the insulator which is present in between the conductors. For air, the dielectric strength, that is the maximum electric field that can be held without any breakdown, is 3 into 10 raised to 6 volts per meter. Okay, for which we can have a condition where the distance d square is very much less than the area of the conductor we have to maintain. Okay, for distance d is equal to 1 centimeter, the potential which can be held or the potential difference between the two conductors is 3 into 10 raised to 4 volts. Okay, these are all 1 markers. And this particular definition you have to remember so that you can understand that for air, what should be the electric field, maximum electric field that can be held or can be held between these two conductors such that there is no leakage, there is no breakdown. That value has to be remembered by you for the electric field and for 1 centimeter the potential difference. Fine. Okay. because how much the charge, that much the electric field, and that much is the potential difference. How much electric field can be held for air is this much, which is called as the dielectric strength. Fine. So these are the points and the formula which you have to remember as a basic for capacitance of a capacitor. Take a pick and note down the values. Fine. Now let us consider a parallel plate capacitor and find out the formula or the dependence of a capacitance of a capacitor on its dimensions of shape, size, and the distance between the parallel plates which we have considered for a capacitor. Now we have here an arrangement of two parallel plates, 1 and 2, with a distance of d between them, and the area of each plate is A, where the electric field between the two conductors is E. Okay, that is what is an arrangement which is a parallel plate capacitor looks like. Followed? Okay, now here we have considered a region 1, a region 2, and a region 3 which is between the two plates. So let us say here the charge is Q plus Q, here the charge on the plate is minus Q, here is the surface charge density on the plate is sigma, surface charge density on this plate is negative sigma. Okay, A is the area and D is the distance between the two plates. That is already known to us in C. Now let us see that for the region 1 and the region 2, is this electric field available or no? So and let us also consider a condition in which D square is very much less than A. Okay, and Q is the charge on each plate. A is the area, surface area of each plate. Sigma, surface charge density of each plate. Okay, and in between these two plates at present we are talking about air, which is the insulator. So now let us see whether in region 1 there is an electric field. Is it there? Is it not there? So let us talk about this plate and a point P in region 1. What will be the electric field due to these charges? Upwards. I can say E1. Fine. And due to these negative charges from this point, because this point P is here and this is the negative, from the point P towards the negative plate, the direction of the electric field towards this plate from the point will be downwards. So E1 and E2, what is E1? E1 is equal to sigma upon 2 epsilon naught. E2 is also sigma upon 2 epsilon naught. But the directions of E1 and E2 are opposite. So E is equal to E1 plus E2 according to the principle of superposition. The directions are opposite, so we write so the electric field at the point P in the region 1 is 0 for region 1. Similarly, let's go to region 2. Okay, let's go to a point CQ. Due to the plate 1 is downwards. The direction of electric field due to the plate 2 is upwards, E2. Okay? Why? For the charges positive radially outwards, for charges negative radially inwards from the point. The point Q is here. So the directions of E1, E2 are opposite in the region 2. Again, what is the value of E1? Sigma upon 2 epsilon naught. E2, that is also sigma upon 2 epsilon naught magnitude. But when we add vectorially, because the directions of E1 and E2 are opposite to each other, we get sigma upon 2 epsilon naught minus sigma upon 2 epsilon naught to indicate that the directions are opposite. So E is equal to 0 for the region 2 also. So above the plate 1 and below the plate 2, the electric field is 0. Now we will talk about the electric field between the two plates. Fine? Okay. So now let us move so that even this part of the board and that part of the board is seen along with the diagram. Fine? Okay. So here we are now going to the region 3, that is the center between the plates. Between plates. Fine? Okay. So now what can we write for E1? E1 is equal to sigma upon 2 epsilon naught. E2 is also sigma upon 2 epsilon naught, that we already know. But we have to now find out the direction of E1 and E2 at a point, say, R, between the plates. So for E1 towards the point, from positive charge towards the point. E2 from the point towards the negative charge. So E2. So as you can see, the directions are same from conductor 1 to conductor 2. So what should I do here? E is equal to E1 plus E2 by principle of superposition. Their magnitudes have to be added up because the directions of E1 and E2 are same. So sigma upon epsilon naught is the electric field between the two plates. Fine? Okay. Now sigma is equal to surface charge densities Q upon A. So just substitute it in E is equal to sigma upon epsilon naught. We get Q upon A epsilon naught. Let us name this as equation 1. Yes? Okay. Now we also know, and what is its direction from plate 1 to the plate 2? That is its direction. Okay. Then V is equal to ED. The potential formula which we have already derived in this chapter only, V is equal to ED. Now E I have got, so let me substitute E in this equation. V is equal to ED. We get V is equal to Q upon A epsilon naught D, where E I have substituted as Q upon A epsilon naught and D I have written as it is. So this is the equation number 2. Now in the previous page we have learned the formula of the capacitance C is equal to Q upon V. Substituting the equation 2 in the denominator, we get Q upon QD upon A epsilon naught. So this portion is the substitution of V from the equation 2. Then we write its reciprocal, Q multiplied by A epsilon naught by QD, where Q cancels, and we get capacitance C is equal to A epsilon naught upon D. Fine? Okay. This epsilon naught, where epsilon naught throughout is the permittivity of the electric field E in air. We can place, other than air, we can place dielectrics, polar, non-polar. We will see that in the next video, and this value will change. So as of now, remember the capacitance C depends on the area of the plate and the distance between the plates. Epsilon naught is a constant which we know the value from chapter number 1. Fine. Okay. So going through a quick revision of what we have done to derive this formula is we considered a point in region 1 for the electric field. We got E is equal to 0. In region 2 also E is equal to 0. But between the plates in the region 3 we can say the electric field is sigma upon epsilon naught. Then sigma we substituted, got equation number 1 for E. We got equation number 2 for V, and substituted these values in the formula of capacitance. C is equal to Q by V, and got C is equal to A epsilon naught by D. So take a pic of what we have learned just now so that this concept is understood by you completely. Yes? And you should be able to follow it as it is.